Hey everybody, welcome back to Trigonometry. Today we're in section 5.5 and this is our last section of identities. So these are the double angle identities. And today I'm going to show you the double angle identities. We will use them to calculate some exact function values, and then we will also use them to prove some identities. So here we go. Now, the double angle identities are really just our old A plus B identities simplified for the special case where A and B are the same angle. So if A and B are the same angle, that means A equals B, and that means A plus B would be the same as A plus A, but we could write that as 2A. So that's where the double angle identities get their name, is because they all have an argument of 2A. So let's start by using our old A plus B identities to derive new identities for the cosine of 2A, the sine of 2A, and the tangent of 2A. Now we're going to start with the cosine of 2A, and this one happens to have three forms, so we're going to find all three. We start by looking at our old cosine of A plus B identity. And you'll remember from section 5.3 that the cosine of A plus B is equal to the cosine of A times the cosine of B minus the sine of A times the sine of B. Now, what would happen if A were equal to B? Well, then we would restate this identity, but everywhere we have angle B, we would now replace that with angle A. So that would look like this. The cosine of A plus A is equal to the cosine of A times the cosine of A minus the sine of A times the sine of A. And of course, this can be simplified. On the left side, where we have the argument, A plus A could be restated as 2A. We just combine like terms. On the other side of the equal mark, cosine of A times cosine of A would be restated as cosine squared A, and then we still have our minus sign, and then the sine of A times the sine of A would be restated as sine squared A. So that is one form of the identity for cosine 2A. Now let's see if we can find another form of this identity. So let's look at the result we already have. Cosine of 2A equals cosine squared A minus sine squared A. And when you think about it, you'll notice that this looks a little bit like one of our Pythagorean identities. Now, it's not actually one of our Pythagorean identities because that would have said sine squared A plus cosine squared A. And we have a minus sign here. But we can't help but notice the resemblance. And we could, if we wanted to, make a Pythagorean substitution for either one of these terms. Let's start by looking at that old Pythagorean identity, sine squared A plus cosine squared A equals 1. If we were to isolate the sine squared A term by subtracting cosine squared A from both sides, you know that that would give us sine squared A equals 1 minus cosine squared A. And since that's true, why could we not replace sine squared A with its Pythagorean equivalent here? Let's do that. So now we're going to recopy this line, but instead of copying down the sine squared A, we're going to replace that with 1 minus cosine squared A, and I'm going to write it in parentheses because both terms are subject to this minus sign here. So here we go. Cosine of 2A equals cosine squared A minus parentheses 1 minus cosine squared A. We're going to distribute this minus sign, and you know that's going to remove the parentheses and change the signs of both terms. So now we're going to have cosine of 2A equals cosine squared A minus 1 plus cosine squared A. Now we can combine like terms. So we see that we have 1 cosine squared A plus 1 cosine squared A. Together they make 2 cosine squared A. So now we're going to have cosine 2A equals 2 cosine squared A minus 1. And this is the second form of our cosine 2A identity. Let's now do the same thing. So we'll start again with this first form that we found. But this time, instead of replacing sine squared a with its Pythagorean equivalent, let's replace cosine squared a with its Pythagorean equivalent. Okay, so what would that look like? If we go back to our original Pythagorean identity and we isolate the cosine squared a term by subtracting sine squared a from both sides, then that would give us cosine squared a equals 1 minus sine squared a. You remember all of that from section 5.1. So now we're going to recopy our cosine of 2a identity, but this time instead of writing cosine squared a for this first term, we'll replace that with its Pythagorean equivalent 1 minus sine squared a. So we're going to have cosine 2a equals 1 minus sine squared a, then minus sine squared a. Now notice that I didn't put it in parentheses this time because I didn't need to, because there was not a negative in front that needed to be distributed like there was over here. And now we're going to combine like terms. So minus 1 sine squared a minus another 1 sine squared a will give us minus 2 sine squared a. So on the next line we have cosine 2a equals 1 minus 2 sine squared a. And that's our third form for the cosine of 2a. Now let's do the same thing for the sine of 2a, and you'll be glad to know that there's only going to be one form this time. So let's start by looking at our sine of a plus b identity. You remember from section 5.4 that the sine of a plus b is equal to the sine of a times the cosine of b plus the cosine of a times the sine of b. Now, if a is equal to b, we can restate the identity, but in place of b, we'll have a. So that would give us sine of a plus a equals sine of a times cosine of a plus cosine of a times sine of a. And of course, we can clean this up a little bit. So a plus a in the argument here would give us 2a. So we'll write sine of 2a. On the right side, we have sine of a times cosine of a for the first term, and really for the second term. Even though the factors are in a different order, they are the same two factors. So we have one of these plus another one of these, and that gives us 2. So we're going to write 2 sine of a cosine of a. And that really cannot get any simpler, so that's the only form we have for the sine of 2a. Now let's get the identity for the tangent of 2a. We will start by looking at our tangent of a plus b identity. So we have tangent of a plus b equals tangent of a plus tangent of b all over 1 minus tangent of a times tangent of b. And again, if a is equal to b, we can replace b with a in our identity. So that would give us tangent of a plus a equals tangent of a plus tangent of a all over 1 minus tangent of a times tangent of a. And when we clean up this time, of course, a plus a gives us 2a, so we'll write tangent of 2a equals, then on the other side of the equal mark in the top, we have 1 tangent a plus 1 tangent a. Those add up to 2 tangent a. Then in the denominator, we have 1 minus tangent a times tangent a. Of course, that's tangent squared a. So we'll have 1 minus tangent squared a. And that is the only identity we have for the tangent of 2a. Now let's catch our breath a little bit and write down all the identities we've found so far so we have them all collected in one place. The first form of cosine of 2a that we found was cosine squared a minus sine squared a. And then we found that cosine of 2a is equal to 2 cosine squared a minus 1. And then we found that it's also equal to 1 minus 2 sine squared a. For the sine of 2a, the only form we found was 2 sine of a times cosine of a. And for tangent of 2a, the only form we found was 2 tangent a over 1 minus tangent squared a. Of course, you are not responsible for memorizing these because they are all on your identity sheet. but it is good to be really familiar with them. So take a look, study them a little bit, and get to know them. Now let's take a look at example 1 together. It says, given that the cosine of theta is equal to 3/5 and the sine of theta is less than 0, find the sine of 2 theta, the cosine of 2 theta, and the tangent of 2 theta. Now, honestly, to me, this is 3 examples all rolled into one because we're finding 3 different values here. Let's start by working on the sine of 2 theta. So, of course, anytime we're using an identity to calculate a value, we need to start by looking at that identity. So the sine of 2 theta we know is equal to 2 times the sine of theta times the cosine of theta. And then we want to look at our given information and see what we already know and what we'll have to find out. So you can see here that we were given the cosine of theta and we don't yet know the sine of theta to plug in. So we're going to write 2, leave a blank for the sine of theta because we'll have to find that out. And then the cosine of theta we know is 3/5. Now let's come over here on the side and draw ourselves a diagram for theta. They told us that the cosine of theta was positive 3/5, and they also told us that the sine of theta was negative. So that limits us to quadrant 4. I'm going to draw a quadrant 4 angle here and call it theta. Now, by telling us that the cosine of theta is 3/5, of course, they've given us the horizontal side and the hypotenuse. So when we close up our triangle, the horizontal side will be 3 and the hypotenuse we can label as 5. Since the hypotenuse is 5, we know the missing side is 4 because we recognize this 3, 4, 5 triangle here. And now because this is a 4th quadrant angle, we know its sine value has to be negative, but that was also given in the problem. So the sine of theta will be negative y over r, which is 4 over 5. So let's go ahead and put negative 4 over 5 in the blank that we left for sine of theta. And now all we have to do is multiply this out. So multiplying top times top and bottom times bottom, 2 times negative 4 times 3 would give us negative 24 for the top. And in the bottom, of course, we don't have a denominator written here, but we know it's 1. 1 times 5 would be 25. And so the sine of 2 theta is negative 24 over 25. Now we're going to calculate the cosine of 2 theta, and you know that we have 3 different versions of this formula. So you want to choose the version of the formula that is the most convenient to use. Now in the problem, the only value that they gave us was that the cosine of theta equals 3/5. So I would choose to use the version of the formula that only requires me to know cosine of theta. That would be 2 cosine squared theta minus 1. But of course we did calculate the sine of theta, so you could use any of the 3 versions you want to, but here I'm going to stick with 2 cosine squared theta minus 1. So that only requires us to know one ingredient, the cosine of theta, which we know is 3/5. So let's plug that in here. We'll have 2 times 3/5 squared minus 1. So the cosine of theta was 3/5 and it's squared, so we have this exponent right here. Now to evaluate this, of course, we need to start by evaluating this power. 3/5 squared is 3/5 times itself, so that would be 9 over 25. So now we have 2 times 9 over 25 minus 1. Next, we need to do the multiplication. So 2 times 9 over 25 would be 18 over 25. And then we need to subtract 1, but we know that in order to do that, we're going to need a common denominator. So 1 is equal to 25 over 25. So that's what I'll write here. And then 18 over 25 minus 25 over 25 is negative 7 over 25. So the cosine of 2 theta is negative 7 over 25. Now for the last part of example 1, we'll need to find the tangent of 2 theta. So let's start out by looking at the identity for the tangent of 2 theta. The only ingredient that we will need to plug in here is the tangent of theta. Now I've got our diagram over here, and we've already figured out the sine of theta, but we have not yet figured out the tangent of theta. We can do that now. So we know that theta is a 4th quadrant angle. That means it's going to have a negative tangent value. and tangent is y over x. So the tangent of theta is going to be negative 4 over 3. Let's come over here and plug that value in place of tangent of theta. So the top of our formula here will be 2 times negative 4/3, and then we have a fraction bar. In the denominator, we have 1 minus tangent squared theta. So that's going to be 1 minus negative 4/3 squared. Okay, now you can see that we've got complex fractions here. So to simplify this, let's start by doing the fraction multiplication in the top. 2 times negative 4/3 would be negative 8/3. Then we have our fraction bar. Then in the denominator, we have 1 minus this fraction squared. So when we square this, negative 4/3 times negative 4/3 is going to be positive 16 over 9. So now in the denominator, we have 1 minus 16 over 9. At this point, we are ready to simplify our complex fraction. So we want to look at the little denominators and figure out what we have to multiply by in the top and the bottom to cancel out both of these denominators. Now the denominators are 3 and 9. So the smallest number that both of those can go into, of course, is 9. So we will multiply this whole thing by 9 over 9. That means we multiply the top term by 9 and both terms in the bottom by 9. And this is what it looks like. Okay, now in the top, we have 9 over 3, and that's going to reduce to 3. Then negative 8 times this 3 would be negative 24. In the bottom, for our first term, we have 1 times 9, that's just 9, and then we have a minus sign. And then for the second term, the 9's divide out, and we're left with minus 16. Then in the denominator, 9 minus 16 is negative 7. So now we have negative 24 over negative 7. And of course, negative divided by negative is positive. So we end up with positive 24 over 7. Now I think it was important for us to find tangent of 2 theta using this identity, because sometimes you will have to use it. But I do want to just point out to you that this time there was a shorter way, because we had already done the hard work of calculating sine of 2 theta and cosine of 2 theta. So we could have used the quotient identity. We could have remembered that the tangent of 2 theta is going to be equal to sine of 2 theta over cosine of 2 theta, because we had already calculated both of these values. Sine of 2 theta we had already found was negative 24 over 25, and in the denominator, cosine of 2 theta we had already found was negative 7 over 25. Now to do this division, we know that to divide by a fraction means to multiply by its reciprocal. So that would give us negative 24 over 25 times negative 25 over 7. At this point, the 25's divide out. Negative times negative is positive, and we're left with 24 over 7. So you can get this same result two ways. This way looks a little easier, but it was only easier because we had already done all the hard work of finding sine 2 theta and cosine 2 theta. But you do have choices. Now here's example 2, and this is exactly the same type of problem as example 1, only the given information is a little different, and maybe some of our algebra steps will be a little more complicated because there is a radical involved here. Otherwise, it's the same strategy. So it says, given that the sine of theta equals negative square root of 5 over 7, and the cosine of theta is negative, find the sine of 2 theta, the cosine of 2 theta, and the tangent of 2 theta. So again, let's start by finding the sine of 2 theta, and to do that, we want to look at the identity for the sine of 2 theta. And now let's go through the identity and plug in what we know and leave a blank for what we don't know. So of course we have 2 here. The next ingredient is sine of theta. We were given that in the problem, so I'll plug that in. And then the last ingredient is cosine of theta, which we do not know yet, but we have enough information to find it. So let's come over here on the side and draw ourselves an angle theta. Now they told us that the sine of theta was negative, and the cosine of theta is less than 0, which means it's negative as well. So that limits us to quadrant 3, so let's draw a quadrant 3 angle. And let's close up our little triangle here. Now telling us the sine of theta is negative square root of 5 over 7 means they've given us the value for the vertical side of the triangle and the hypotenuse of the triangle. So the vertical side is square root of 5, the hypotenuse is 7. Now, in order to find the cosine of theta, we'll need to know the horizontal side of the triangle, and in order to find that, we'll have to subtract these two squares. So x squared is going to be 7 squared, which is 49, minus square root of 5 squared, which is 5. Then 49 minus 5 is 44. So we have x squared equals 44. That means x equals square root of 44. Now this radical can be reduced because 44 is 4 times 11. The square root of 4 is 2, and then the 11 stays under the radical. So now the cosine of theta is going to be negative, because this is a third quadrant angle, x over r. So that's going to be 2 square root of 11 over 7. And let's plug that cosine value in over here in our formula. Now to multiply all this together, of course, we'll do top times top, bottom times bottom. And in the top, we'll have to do the signs, then the coefficients, then the radicals. So here we go. Negative times negative is going to be positive. And for the coefficients, 2 times 2 is 4. And then for the radicals, square root of 5 times square root of 11 is square root of 55. In the denominator, it's just 7 times 7, so that's 49. So now we have sine of 2 theta equals positive 4 square root of 55 over 49. Now, every now and then, somebody will pause here and say, wait, should we not have gotten a negative number? Because this is a third quadrant angle. And if you're thinking that, then I like the way you're thinking, because you're looking back at the information you already have and making sure everything fits together. So that's good. But remember that this diagram is for theta. So theta is a third quadrant angle, but what we calculated here was the sine of 2 theta, which is not a third quadrant angle. So it's okay for the sine of 2 theta to be a positive value. And now let's calculate the cosine of 2 theta. And this time, because the value given in the problem was the sine of theta, let's use the version of the identity that only requires us to plug in the sine of theta. So that's going to be 1 minus 2 sine squared theta. So now when we plug in our known value, we'll have 1 minus 2 times negative square root of 5 over 7, all squared. Now to work this out, let's evaluate the square first. So negative square root of 5 times itself would be positive 5, and in the denominator 7 times itself would be 49. So now we're going to have 1 minus 2 times 5 over 49. And now for the multiplication, 2 times 5 over 49 would be 10 over 49. So now we have 1 minus 10 over 49. Of course, to do this subtraction, we need a common denominator, so we'll change the 1 to 49 over 49. Now we have 49 over 49 minus 10 over 49, and that comes to 39 over 49. All right, now to find the tangent of 2 theta, we know that we're going to use our tangent 2 theta identity, and here it is. We've still got our diagram here showing angle theta, but now we need to calculate the tangent of theta. So I'm going to erase that work, and we know that tangent is y over x, and theta is a third quadrant angle, so the tangent of theta will be positive square root of 5 over 2 times the square root of 11. Now this is one form of the tangent of theta, but of course it's good to have it rationalized as well. So let's go ahead and rationalize this denominator by multiplying top and bottom by the square root of 11. That would give us square root of 55 in the top, and in the bottom, square root of 11 times itself would be 11, and then times 2 would give us 22. So the tangent of theta is square root of 55 over 22. Okay, now when I go back to my formula to plug in my known tangent value, in the top I'm going to use the rationalized version. So that would give us 2 times square root of 55 over 22 for the top of our identity. Then we've got the fraction bar. In the bottom, we're going to have 1 minus tangent squared theta. Now, I could plug in my rationalized version again. So I could write square root of 55 over 22 all squared. But just think about squaring this number. You would have to come up with 22 times itself, and that's going to be a pretty large number. So to avoid that, let's use the unrationalized version of our tangent value. And you'll see that that makes our work a little bit easier. So right here where I'm getting ready to plug in tangent of theta squared, I'm going to use the unrationalized version of our tangent value and square that. Okay, now in the top where we have 2 square root of 55 over 22, we know that 2 over 22 will reduce because both of these numbers can be divided by 2. So when we do that, that leaves 11 in the denominator. So for the top, we now have square root of 55 over 11. In the denominator, we still have 1 minus this squared value. So now when we square this, square root of 5 times itself will be 5. And in the denominator, 2 square root of 11 times 2 square root of 11 would be 4 times 11. That's 44. Now I hope you can see why plugging in the unrationalized version of our tangent value was easier than plugging in the rationalized one. Because if we had used this rationalized version and squared it, that would have made us write 55 over 484 here, and that would have been much harder to deal with. So this way, when we simplify our complex fraction, all we have to deal with is the 11 and the 44. So we need to pick a number that both 11 and 44 can go into. Of course, that number is 44, so we'll multiply the top by 44 and both terms in the bottom by 44. Now, in the top, 44 divided by 11 will reduce to 4. So we'll have this 4 times the square root of 55. In the denominator, 44 times 1 is 44. Then we have this minus sign. And then we have 5 times 44 divided by 44. And of course, that reduces to just 5. So now all we have to do is finish this subtraction where we have 44 minus 5. That would be 39. And so our final value for the tangent of 2 theta is 4 square root of 55 over 39. And in case you're wondering if we could find the tangent of 2 theta using the quotient identity, of course we can. So we'll just remember that tangent of 2 theta is equal to sine of 2 theta over cosine of 2 theta. And we already had these two values from the first part of the problem. So the sine of 2 theta was 4 square root of 55 over 49. The cosine of 2 theta was 39 over 49. And so to divide by a fraction means to multiply by its reciprocal. So we have 4 square root of 55 over 49 times now 49 over 39. The 49's divide out, and it leaves us still with 4 square root of 55 over 39, just like we got using the identity. Now here's example 3, and this one is different than what we did in the first two examples. So it says find the sine of theta, the cosine of theta, and the tangent of theta if the cosine of 2 theta is 4/5 and theta is between 90 degrees and 180 degrees. Okay, now what's different here is that in the first two examples, they gave us information about theta and asked us to find function values for 2 theta. Now it's the other way around. They're giving us information about 2 theta and asking us to find function values of theta. So to help us with that, I have copied down all of our double angle identities right here. Now, let's start by finding the sine of theta. So we want to find sine of theta, and the value that we know is cosine of 2 theta. So we want to look at our double angle identities and choose the one that involves cosine of 2 theta and sine of theta and nothing else. And so that would be this identity right here. Cosine of 2 theta equals 1 minus 2 sine squared theta. And now we will plug in our known value. We know that the cosine of 2 theta is 4/5. So now I have 4/5 equals 1 minus 2 sine squared theta. And we want to isolate the sine squared theta. To do that, we start by eliminating this 1, so we'll subtract 1 from both sides. That will give us 4/5 minus 1 equals negative 2 sine squared theta. And we know that 4/5 minus 1 is 4/5 minus 5/5. And we know that 4/5 minus 5/5 is negative 1/5. So now we have negative 1/5 equals negative 2 sine squared theta. And now to isolate the sine squared theta, we need to divide both sides by negative 2. On the right side, we'll just put divided by negative 2 like that. On the left side, we already have a denominator, so we don't want to put a new fraction bar. Instead, we can take advantage of the fraction bar that's already there. Because we put negative 2 in the denominator of the right side, we can also put negative 2 in the denominator of the left side. Now, the left side says negative 1 divided by 5 times negative 2. That's negative 1 over negative 10, which we know is going to simplify to positive 1 over 10. And then on the right side, the negative 2's divide out, and that leaves us with sine squared theta on the right. At this point, we have a squared expression equal to a number. And you remember from algebra that whenever you had a squared variable equal to a number, you had to apply the square root property. So we unsquare this expression on the right side. That will give us sine of theta, and that's going to be equal to plus or minus the square root of the other side. So that would be plus or minus the square root of 1/10. Now, we had to put the plus minus sign because of the square root property, but we know that in reality, the sine of theta can't be both positive and negative. It can only be one or the other. So we need to think about what quadrant theta is in and decide whether this sine value should be positive or negative. The problem told us that theta is between 90 and 180 degrees. So we know that theta is in quadrant 2, and we know that sine values are positive in quadrant 2. So we're going to just forget about the negative sign, and we're going to keep the positive. So now we have sine of theta equals positive square root of 1 over square root of 10. Of course, the square root of 1 is just 1. So now we have sine of theta equals 1 over square root of 10. And when we rationalize that denominator, we end up with square root of 10 over 10. So the sine of theta is square root of 10 over 10. Now we want to find the cosine of theta. And of course, because we have already found the sine of theta, we could use that information and a diagram to find any other function of theta that we need to know. But in order to give us a little more practice working with the formulas, let's find the cosine of theta using one of our double angle identities. So this time we want to find the cosine of theta, and we know the cosine of 2 theta. So we want to use an identity that involves only those two values, and that would be this one. The cosine of 2 theta equals 2 cosine squared theta minus 1. So I've copied that here. Let's go ahead and plug in our known value. So the cosine of 2 theta we know is 4/5. So now we have 4/5 equals 2 cosine squared theta minus 1. In order to isolate the term that contains cosine squared theta, we're going to add 1 to both sides. That's going to give us 4/5 plus 1 equals 2 cosine squared theta. Now, before we do any more solving, let's go ahead and do this addition. We know that 4/5 plus 1 is equal to 4/5 plus 5/5. And then we know 4/5 plus 5/5 is going to be 9/5. So we have 9/5 equals 2 cosine squared theta. To isolate the cosine squared theta, of course, we will divide both sides by 2, and that just means putting a 2 in the denominator of both expressions. Now the left side is going to be 9 over 10, and on the right side, the 2's are going to divide out. So we will have 9/10 equals cosine squared theta. Again, we will have to apply our square root property. So we will unsquare this expression and we'll put a plus minus square root on the other side. That will give us cosine of theta equals plus or minus the square root of 9 over 10. Now, we know that a cosine value can be either positive or negative, but it can't be both. So again, we remember that theta is in quadrant 2, and cosine values are negative in quadrant 2. So this time we'll drop the plus and keep the negative. And at the same time, we'll split this single radical up so that we have a radical for the top and a radical for the bottom. That's going to give us cosine of theta equals negative square root of 9 over square root of 10. Of course, the square root of 9 is just 3. So now we have negative 3 over square root of 10. And then when we rationalize that denominator, we'll end up with cosine of theta equal to negative 3 square root of 10 over 10. And now to find the tangent of theta, we look at all of our double angle identities, and your mind might go to this tangent formula. If we want to find the tangent of theta, you might notice that this identity does contain tangent of theta, but in order to use it, we would have to know the tangent of 2 theta, which we don't have. We have the cosine of 2 theta. And it seems like a lot of work to have to find the tangent of 2 theta in order to use this formula to find tangent of theta. Instead, our best bet here is to go to a diagram. So to find the tangent of theta, let's think about what we already know about angle theta. We know the sine of theta is square root of 10 over 10, and we know the cosine of theta is negative 3 square root of 10 over 10. We also know that theta is in quadrant 2. So let's draw ourselves a quadrant 2 angle and close up the triangle. Now, because the sine of theta is square root of 10 over 10, we know the vertical side of our triangle will be square root of 10, and the hypotenuse will be 10. Instead of using the Pythagorean theorem now to find the horizontal side, we already know that the cosine of theta is negative 3 square root of 10 over 10. So that means the horizontal side is 3 square root of 10. Now to find tangent of theta is very simple. We know that tangent values are negative in quadrant 2, so we put down a negative, and we know that the definition of tangent is y over x. That's going to make square root of 10 over 3 square root of 10. Now we would normally think about rationalizing at this point, but instead we're going to be able to divide out the square roots of 10, and that's going to leave a 1 in the top. So that leaves us with tangent theta equals negative 1 over 3. Now here's example 4, and this is a proof for us to work on together. So it says verify that the following equation is an identity. Cotangent of x times sine of 2x equals 1 plus cosine of 2x. And you know that whenever we work on a proof, we always start by copying down the more complicated side. In this case, when I try to think about which side is more complicated, it's really not clear because both sides look about the same to me. But when I think about doing identity substitutions, I know that there's only one thing that I can replace sine of 2x with, and that's the sine of 2x identity. On the other hand, there are 3 different expressions that I could substitute in place of cosine 2x. And it's not clear right off the bat which one is the best one to use. So to avoid having to make that decision, I'm going to work on the left side of the equation. So let's copy down that left side, and now let's think about what we might want to do here. So we have cotangent of x times sine of 2x. It's probably pretty clear that in order to make anything simplify, we're going to have to replace sine of 2x with its identity. which is 2 sine of x cosine of x. And since the other part of our expression is cotangent of x, we'll want to make a change here as well so that we'll have something to work with. So let's use a quotient identity to replace cotangent of x with cosine of x over sine of x. Over here on the right, I'm just going to state that I used a quotient identity. And then I want to replace sine of 2x with its identity, which is 2 sine x cosine x. So again, over here on the right, let's state that we used a double angle identity to make that substitution. Now that we've done that, you can see that the sine x's are going to divide out. So we cross those out and then we state that we reduced. And now that leaves us with 2 cosine x times cosine x, which is 2 cosine squared x. Now, just like we've done before, when we get to a place where we don't know what to do next, we should always look at what we've got and look at what we want to get to. In this case, I've got 2 cosine squared x, and I want to get to 1 plus cosine 2x. So I need to ask myself, do I have an identity that contains a cosine squared x and a cosine of 2x? And of course we do. So let's look at that double angle identity. We know that we have this formula available to us. Cosine of 2a equals 2 cosine squared a minus 1. That's just copied right off of our formula sheet. Now the question is, can we rearrange this identity so that the 2 cosine squared x is isolated? I believe that we can. All that we have to do is add 1 to both sides. And when we do that, we'll have cosine 2a plus 1 equals 2 cosine squared a. That means that 2 cosine squared x can be replaced with this expression over here, which for us would be cosine of 2x plus 1. Now we were able to do that because we used a double angle identity, so you would want to write that over here. And now when we compare what we've got to what we were aiming for, we can see that they are exactly the same. And so this proof is finished. Here's example 5. And again, it says verify that the following equation is an identity. We have tangent of 2 theta equals negative 2 tangent theta all over secant squared theta minus 2. Now at first glance you might think this looks pretty bad, but it's actually not as bad as it looks. Notice that the left side is just a double angle expression. And so we can start by working on the left side, and we'll just take that tangent of 2 theta and replace it with the tangent of 2 theta identity, which is 2 tangent theta all over 1 minus tangent squared theta. I'm just going to write down here that I used a double angle identity to do that. And I'm not going to do any more work on the left side. Let's just leave it like that. And let's try to make the right side look like this tangent of 2 theta identity. So now I'm going to start on the right side. And I'm going to copy down the right side of our equation, which is negative 2 tangent theta over secant squared theta minus 2. Now let's look at what we've got and let's look at what we're aiming for. You can see that in the top we have negative 2 tangent theta, and we are aiming for it to be positive 2 tangent theta. So yes, a sign change is going to have to occur somehow, but it's good news that the top of what we have already contains the 2 tangent theta that we need it to have. In the denominator, we have secant squared theta minus 2, and we're going to want it to say 1 minus tangent squared theta. So I want you to ask yourself, do we have an identity that links secant squared theta to tangent squared theta? Probably immediately you say, yes, we do have an identity that does that, and it's one of our Pythagorean identities. So let's circle secant squared theta in the denominator, and let's replace that with its Pythagorean identity. We know that 1 plus tangent squared theta is equal to secant squared theta. So let's make just that one change. The top will still say negative 2 tangent theta. In the bottom, we will replace secant squared theta with 1 plus tangent squared theta, and we will still have this minus 2 right there. On the other side of the proof, let's write down that we used a Pythagorean identity to make that substitution. Now look again at the denominator. We have some like terms that we can combine. We have a positive 1 and a negative 2. We know that 1 minus 2 is negative 1. So I'm going to copy my top just as it is, and in the denominator, 1 minus 2 will make negative 1, and then we've got this plus tangent squared theta. Over here on the other side, let's just state that we combined like terms. Now compare what we have to what we want it to look like, and I think you'll see we're in pretty good shape. We want the top to say positive 2 tangent theta, but right now it says negative 2 tangent theta. We want the bottom to contain 2 terms, which it does. And we want the terms to be positive 1 and minus tangent squared theta. But the terms that we have are negative 1 and positive tangent squared theta. So I think you'll agree with me that these are all the right terms, but they are all the wrong sign. So the easy way to fix that is to multiply the top and the bottom by negative 1. So over here on the other side, let's state that we are multiplying by negative 1 over negative 1. That's allowed because that's nothing but 1. We can always multiply by 1. So now when we do this, negative 1 times the top will give us positive 2 tangent theta, and negative 1 distributed through the bottom will give us positive 1 minus tangent squared theta. And that is an exact match for what we have on the left side, and that means this proof is finished. And now let's look at part B together. This will be our last example for this section. It says verify that the following equation is an identity. We have 1 plus cosine of 2x all over sine of 2x equals cotangent of x. Now, if you think about it, you'll notice that these are the same components we saw in example 4, but because this equation is arranged differently, we will have to approach this a different way. Clearly, in this case, the left side is the more complicated side, so let's start by copying that down. And you can see that both of the functions here have double angle arguments, but the right side is just cotangent of x. So we are going to have to make some identity substitutions here in order to eliminate these arguments that say 2x. Of course, when we think about the cosine of 2x, there are 3 different identities that we could replace this expression with. So let's look at those. We know that the cosine of 2x is equal to 2 cosine squared x minus 1, or 1 minus 2 sine squared x, or cosine squared x minus sine squared x. Now, to tell you the truth, any of the 3 of these would eventually let you simplify so that you get cotangent of x. Any of the 3 will work, but let's be smart about this. We can see that currently in the top we have 2 terms, and we're going to want to end up with cotangent of x, which probably means that at some point we're going to get this expression to simplify to cosine of x over sine of x. So at some point, this positive 1 is going to have to disappear. Do we have an identity that will help us with that? And yes, we do. We see that we could replace cosine of 2x with 2 cosine squared x minus 1. So let's go ahead and do that. If we make that substitution, we would still have 1 plus here in the top, but this cosine of 2x would be replaced with 2 cosine squared x minus 1. Then in the denominator, we're going to want to replace sine of 2x with its identity, which is 2 sine x cosine x. Over here on the right side, let's state that we used double angle identities to make both of those substitutions. Okay, now in the top, the 1 and the minus 1 will add up to 0, so I'm going to record that over here on the right. And that leaves us with 2 cosine squared x in the top and 2 sine x cosine x in the denominator. Now we want to think about simplifying. So we can see that the 2's will divide out. We can also see that one of the cosines in the top is going to divide out with the cosine in the bottom. Over here on the right, let's state that we reduced. And that leaves us with cosine x over sine x, which we know can be restated as cotangent of x because of our quotient identities. And now we have simplified the left side so that it looks exactly like the right side. And so this proof is finished. Okay, everybody, that is the end of section 5.5, and it's also the end of our whole chapter on identities. So I know that most of you have been working really hard on your identities. I know that this is a challenge for everybody the first time that they see it. Trust me that your hard work does pay off. If you are going into calculus, what you have learned here in chapter 5 is going to be invaluable to you. But even if you're not taking calculus, the thinking skills that you have picked up by working through these proofs, you don't even know yet how much this is going to benefit you in your everyday life. Not that you'll be solving proofs all the time. Of course, you won't be solving proofs. You may never see another trig function the rest of your life after you finish this course. But learning to write proofs and justify your reasoning is an excellent way to sharpen your critical thinking skills, and that's something that will help you in every walk of life. So I hope that you're working hard here and asking questions and making progress, but just know that in our next section we are going to be switching gears, and so I'll see you next time for section 6.1. Bye now.